Oh, I need to share my screen to you guys. Let's see, share the screen. There's only one to share. There we go. All right, so now I got to start a new PowerPoint. Yeah, and you can turn off your speakers too, please, because you can just hear me, right? Because again, it's going to drive us nuts, especially if it starts feedbacking. So we want a new one and standard lecture, create, and new slide, and blank. So we go here, Control C, we'll just make a bunch of pages. And all right. So, what happened to Mr. Oh, I didn't plug in the tablet. So now we got to wait for the tablet to handshake. It's always something. Always something. Okay. Of course, you should have your notebooks open, ready to go, right? Always have your logbooks open in this room. It's the first thing you should do when you get here. Give me a few minutes to get my lunch going on. Yeah. Taking its time. Let's see. Minimize this guy. Oh, still not ready to go. What if I start the, what is that? Oh, that's weird. How do I get my start menu? Good. Now it's handshaked. Very good. Okay, so first of all, so we got our lab 9 impedance. And so our objectives is that we're going to learn about the general definition of resistance, which so we call. I mentioned it before. So instead of saying R, we're going to call it Z. Impedance is, and instead of calling it resistance, we call it impedance. And it's defined as some real part times some imaginary part times a thing called the reactance. And you might remember that I called capacitors and inductors reactive elements. And we're going to use a voltage divider to measure Z's of different components. Well, in fact, we're going to do that, but you get the actual Z or excuse me. Yeah, and then you have different components, and then we can extract the value L or C, the inductance or the capacitance. And we're going to learn about what's called Bode plots. So this is beyond the lab, but the lab is written in some kind of academic way, and I'm going to make this practical, like I do in my basic electronics class. I'm going to learn about how engineers and everybody else and scientists actually use these things. And we're going to introduce ourselves to high and low pass filters. And we're going to learn about a tuning circuit. And that's going to use something called resonance, which I didn't quite get to in lecture. I will on Thursday. Today we're not going to background all of this right now. We're going to just background a little bit, and then we're going to take some data, and then next week I'm going to get into more nitty-gritty for the background. Okay, so now, what's that all about? Anybody want me to go back? Okay, so let's do some background. So first thing we'll do is we'll review a two-element voltage divider. We've used it over and over again. And so in the standard form, we have a V-in terminal. We have some, and we're going to use the letter Z now, some Z-in. We have a V-out terminal. And then we have Z2. And that's the ground, the return. And so, of course, all voltages are referenced to some ground. This is usually left out. But that would be the black connector, for example, on the oscilloscope. So, if you stare at this thing, you see that V out equals to the current times Z2. Very simple, right? IR drop. Of course, things that look like the drawing is complicated, and now I'm telling you this very simple circuit. And of course, it's not quite that easy. Clausewitz said that the things you need to the goals of war are very simple, but the steps are incredibly difficult. I hope this is not incredibly difficult. Now, we notice that Z1 and Z2 are in series. So, side note, the Z rules of combination, so you might want to write that out so you know what you look at this later. The rules of combination for impedances are the same as resistors. So if they're in series, Z total equals Z1 plus Z2. And we're going to learn that this is true even if Z2 is a capacitor. Remember, we've learned a rule of combination for capacitors that's the opposite of resistors. But engineers don't like shit like that. So they made up this definition. So no matter what the circuit elements are, you can use these same rules of combination. And we also, since we know that I total is always equal to V total over R total. Well, excuse me, Z total. Always, always, always. So we see that, and from now on, we're going to call V total V in. So we see that V out is going to equal to V in divided by Z total times Z2. Well, that didn't work very well, did it? Oh, good. That worked. All right. So we had V out equals to V in over Z total times, total times Z2. Is everybody cool with V out being the voltage across Z2? Should I go over that? Because there's a voltage you have, remember, it's series, right? So circuit rules, the basic circuit rules said that we have a delta V1 and we have a delta V2, and V in has to equal delta V1 plus delta V2, right? And so we also know that I is the same for everybody in a series circuit. Excuse me. So V in, if we're measuring this, remember that's going to ground here. That's simply the power supply. And we see that there's going to be a voltage drop across Z1. And so V out is, of course, at this point, because remember, wires don't have any resistance. So you could say that V2 is equal to V in minus delta V1. But, that's just sort of, we're chasing our own tail. There's some voltage, and the voltage drop across Z1 is going to be V out. Give me a minute. No, it isn't. But it's what creates V out. We can't, if we know delta V1, we still got to use the V in and do the subtraction to get the voltage out. But it's so much easier. We're measuring. It's just like when we put the resistors in series and parallel, right? You can just put your voltmeter on either side of the resistor and you measure the voltage in that resistor, right? It's very straightforward. And with Ohm's law, we know that that V out, in the way we see it, right? We have to define our space, and it's I total times Z2. All right, so now the way this is done, and I'll get into more various reasons why, we always express this as a ratio. So then we get Z2 over Z1 plus Z2. Pretty trivial, right? All right. So what we usually do, we're gonna, whoa, no, that happened. So we set this up and we label it slightly differently. We got our V in. We have some Z here, and this one here, Z1, is usually some standard, well known, aka well known. And once again, we have our V out. And then here, what we do is we call this, remember, it's just circuit, it's a circuit element. But we're going to give it a special name. We're going to call it the device under test. So we can put a device there, and we can take a series of measurements, and we've done it before. We know how to rearrange this so we can get Z2. We can extract Z2. So if we know Z1, we can get Z2. And we'll go over that. But for now, we're going to stay in this V out over V in. And this is what engineers plot. So in the vein of gonzo physics, what we plot is frequency and V out over V in. And in fact, what we do, a Bode plot, is we plot the log of F and we plot the log of V out over V in. And that's what's called a Bode plot. And this applies to lots of things like mechanical engineering and electrical engineering, civil engineering, because you can define impedances to various things. So we go back to our definition of impedance. So we can now say, all right, the impedance, the reactance of a capacitor is minus 1 over omega C. And we should remember that omega equals 2 pi F, frequency, because our function generators, and it's easier, are calibrated in hertz, not radians per second. And also when we measure time, and then also remembering that frequency equals 1 over the period. So we express that as 1 divided by 2 pi C, capacitance. And then for an inductor, it equals omega L. Notice that it's not negative omega L, it's just omega L, which is 2 pi L. Oh, sorry, yeah, 2 pi F. Excuse me, 2 pi F L. Duh. Now, you may have heard me mention, and you may have noticed it from the oscilloscope lab, that what this means is that inductors and capacitors are frequency-dependent resistors. Excuse me. So, just as a little bit of a glimpse of next week, what happens is that, and in principle, you guys know about the complex plane, real and imaginary. So notice the plus and minus, that an inductor, the reactance of an inductor points up, and the reactance of a capacitor, the reactance of a capacitor points down. And we're going to learn in lecture on Thursday that there's a special condition where the two of them are equal, and you notice that then if they're in a circuit, they would cancel each other out, and that's what's called resonance. But we're going to get to that. Excuse me. Okay, so today what I'd like to accomplish is that we're going to wire up our voltage divider. Oops, too much. And we're going to be examining capacitors today. So remember, V out over V in. And when it comes to just, it was negative. We can drop the negative sign for the moment. I'll get into that more next week. So remember, it's Z2 over Z1 plus Z2. And that's going to be 1 over 2 pi FC divided by R plus 1 over 2 pi FC. Now, also, I forgot to mention the units are ohms. So you stare at this, both Z2 and Z total vary with frequency. Now, another thing is that if I, wait a minute. Something just was passing through my head, and sorry. So the greater is Z2, the bigger, oh, right. So if I plot V out as a function of Z2, we expect something like this. So if Z2 gets bigger, we expect Z out to get bigger, V out, and of course we also expect V out over V in to get bigger. Of course, it's not exactly obvious, but we can have faith that if Z2 is bigger, V out has to be bigger. Because what happens is you're looking at a ratio, sort of, a ratio of Z1 and Z2. And so the delta V1 plus delta V2 has to equal V total. So I Z1 plus I Z2 is V total. So you see that Z1 is fixed. Excuse me. Z2 is going to get bigger. The current's going to change, but they both have the same current. But Z2 gets bigger, so V2 has to get bigger. Now, you might also notice that for a capacitor, if I plot frequency and its reactance, which in this case is going to be Z2, remember it's 1 over 2 pi FC. So that means that at low frequencies, this is going to have a high reactance, and this is going to be a hyperbola because it's 1 over F. And the higher in frequency I go, the lower is my reactance of my capacitor. Let me write that. Okay, so when we look at this circuit that we just had, this is, this is called a pass filter, a band pass filter. Of course, it could be a high pass or it could be a low pass. That's going to be something you're going to figure out. I've given you enough tools. And the other way is now I put the capacitor here and I put the resistor here, the R standard. Of course, that's Z1 and that's Z2. But don't forget, now this is going to become Z1. And now we're measuring the voltage across our standard. So here's what we're going to do. We're going to have a table of frequencies. And for both circuits, and I you know what, I don't have it in front of me. I'll have to see if I can resurrect this. But I recall something like 200, 500. I'll go look. And for each frequency, you're going to measure V out and V in. And you're going to make two tables today for each of these two circuits. Two circuits, two tables. So one thing, it's very important that you always measure V out over V in. Why? So I know that our Z standard is very low, 10 ohms. Okay. So this is only 10 ohms. And if we had the capacitor here at high frequency, that means that Z of the capacitor could be on the order of 10 ohms. And that would mean that the input Z, we've talked about input impedance. Remember, the analog voltmeter has an input impedance of 10K. The digital voltmeter has an input impedance of 10 meg. And the reason is that when we take a voltage measurement, one will have less effect. Now, if I have an input Z of only 20 ohms, V in is going to sag because there it is. It's going to sag because remember, signals are power, voltage times current. Your function generator is only guaranteed to, if you set the amplitude at 10 volts, it's only guaranteed to deliver that to 50 ohms. So if I try to drive 20 ohms, the function generator is not able to supply enough current. So V out is going to sag, V in is going to sag, and hence V in as well. So if V in is going to sag and also V out, so you take the ratio, you're always guaranteed to get the right answer. This is also measurement science. This is you're giving a test tone, which is V in, because we're going to use a function generator, a test tone, and you're looking at the response. Okay, so we know the data table we want. So let's draw a more detailed schematic. So we have our function generator. So we'll say that's the red and that's the black. So we're going to have, first one is going to be a resistor, the R standard. And then, so that's V in. So why don't we okay. So that's going to go there. Then we're going to then wire it to a capacitor. And it's right there. And even you see the value of it. And then we go back to the function generator. The black. Now, we're going to use our oscilloscope and we're going to use channel 1 and channel 2. And remember we have our BNC to banana adapters. So we're going to put channel 1 over here to V1, and channel 2 is going to go to V out. And then, yeah, I think, oh yeah, right, I forgot one thing. So of course, each of them has a black one. It turns out that you only need to connect one of the black ones because they're connected together inside the oscilloscope. And to here. So you'll be able to see V out and V in on the same screen. Now, one thing I want you to pay attention to that we'll discuss next week. So when you look at these things on the screen, of course, you're going to see sine waves. So let's say we have V in. You're going to notice something that you might find a little odd, that the out is not going to lay right on top. And we call this a phase shift. And this has something to do with this complex plane. So in our case, and then of course the real part, I forgot to draw into this thing, forgive me. There's Mr. Cursor, oh yeah. The real part here is R. So it turns out that Z total, well, give me a minute. Yeah, equals to R squared plus, well, that's in this complex plane, but we'll just table that. Don't worry about this just yet. Just this diagram here is important for now. And that is why we have the phase shift. And I'll go into that in more detail next week, and then also in next week's lecture, or even maybe Thursday, because we're going to finish chapter 30. This is chapter 31 stuff. And I find it very fascinating. This is not your primary objective today. What I'd like you to see is where is here's a question you want to answer today. Where is greatest phase shift for this circuit? We'll just do it for the first circuit. Is it at high frequency or low frequency? And then next week we'll explain it. Okay, so what I'm going to do is I'm going to stop this. I'm going to stop the recording. I'm going to dig up the table of frequencies and I'll write them up on the front board. And then you can have at it. Okay. Stop the share. And I'm going to stop the meeting. And I'm going to stop the recording.